Welcome to the stage, Vice President of Launch at SpaceX, Kiko Donchev.
All right, Summit. Hey, guys. So I have the really awesome opportunity to introduce someone who I've known for a long time. He's my mentor. He was my professor in college. He was a partner and someone I work with at NASA. And it's really going to be amazing to talk about the universe and what it means to run a large team and do incredible things. So Dr. Thomas Zurbuchen got his PhD in Switzerland in Bern in '96, after which he moved to Michigan and led space sciences studies there. Also, after doing a bunch of research, he got really into entrepreneurship, actually, and started one of the first university programs for entrepreneurship in the country, the Center for Entrepreneurship at the University of Michigan. But was feeling a little bit like he wanted something more, and he got the unique opportunity in 2016 to effectively leave NASA, or to leave Michigan and go be the head of science at NASA. He spent 6 years there. In that time, he landed a large rover on Mars. He launched the largest telescope humans have ever put into space to help us look deeper and farther in the universe. And he did one of my favorite missions called DART, which was the first planetary protection effort we've ever had, where we actually launched a small satellite into an asteroid and redirect it to help us in the case that a real bad day was coming and something was headed towards Earth. So it's really awesome, and I'm really excited to welcome Thomas to the stage. So please, round of applause for Dr. Zurbuchen.
Thanks, Mike. Well, I'm so excited to be here, and thanks for wearing the Michigan hat. Go Blue. Exactly right. Well, what I really want to tell you is two stories at the same time. One story is one of human exploration, and one story is that of building teams. And what I'm going to tell you is that both are needed to kind of transcend boundaries that are up there. For me, to tell you that story only makes sense if I tell you a little bit about myself. And the story that my life started in is in a little town in the mountains of Switzerland. So there's a lot of amazing things in that town. You're looking there in the center, kind of towards the third on the left at the house I grew up in. Very few houses are there because they're all farmers. In fact, there was not a single student, not a single engineer, a single scientist there. But what I had, the amazing kind of, really what I had is a gift, and that is public school. And I went and did a test, and what could I be if I grow up? And what came out is engineer and scientist. It's like, I haven't met any of those people. What do they do? And so I went and looked at this. The other thing that was so amazing about this home are the dark skies. And I spent a lot of nights on the roof of the house looking at the dark skies, and I learned all the constellations. And not only did I think about the worlds out there, I always wondered, is somebody else looking back at me and thinking about me looking in this direction? And it's that kind of big view of a small town that really transcended my thinking. And I went in this public school, and I had a class, and I did a lot of physics. Eventually, I studied physics. But the class that made me decide to study physics is a class about this gentleman. Of course, that's Copernicus. See, what I learned in that class was a philosophy class, not a physics class. What I learned in that class is that this individual, looking at the data of our universe, not only changed how we think of the universe, but also history itself on Earth. To me, that's mind-blowing. The fact that we can look at nature, we can look at the world around us, everything we know, the boundaries of what we know, and as we transcend these boundaries, we chart a new future. We can, in fact, change how we think about ourselves. Of course, this was the story of him was kind of a sad story because most of what he knew, he only released on his deathbed. Why? Because he knew he was going to get into deep, deep trouble. Because if you tell the bosses of this planet that the planet, which was believed to be in the center of the universe, is not really in the center of the universe, but instead goes around the star, the sun, they feel degraded. They feel like something happened to their power. Not only the kings, but also the popes and the priests, they feel like something bad happened to them. That, about 150 years later, really came to bear when another step happened, and that is when technology entered the market. And of course, what you see here is an artistic depiction of Galileo, who in 1609 put kind of a tube and glass together and built the first telescope. It's not that impressive a telescope, but what he did is he looked over there, and what you see is a document on the right at the University of Michigan Library, you with the Michigan hat, it's right there, and basically what he shows there is that Jupiter, when he looked at Jupiter, that he found celestial companions of Jupiter, that there are other moons of Jupiter, the Galilean moons, as we talked to them about. And he published that work, and of course it got him into deep trouble. Just like what Copernicus worried, he was put on house arrest. It changed his entire life. But what it did, it changed the way we look at the universe. This new technology changed the way we look at the universe forever. I always wondered how that felt. Looking at the sky in a new way and looking at the universe in a new way and figuring out something both about the universe but also about us doing so. And the story I'm telling you is I experienced that. And I experienced that last year when for the first time I looked at data that was scattered by a telescope that was really unusual. The telescope that I'm going to talk to you about is the James Webb Space Telescope. If you look at the mirror, you realize it's not one piece of glass like every other telescope ever built before in space. It's 18 pieces of glass. And of course, the reason for it is that the size of that mirror is 21 feet across. Right now, and I know Kiko and his friends are working on bigger rockets, but right now there's no rockets where you can fit 21 feet across in there. You can say, why would we want to build a universe that big, a mirror that big? And the answer is, the part of the universe we want to observe is something we've never seen, which is the earliest part of the universe, where basically all the signals are really old. So the light is going to be really old. I'm going to talk a lot about time, but it's also mostly in the infrared. So suppose you were out there, and even if your eyes were 21 feet across and you could see into the universe, your eyes would not see it because it's infrared. Your skin is detecting infrared. When you're next to a campfire, you feel the skin detecting heat. So those heat signals need to be reflected. So again, you need a big mirror if you look far away. The other thing you need to do is you need to build a cold mirror. And to build a cold mirror means that you need to protect yourself from all radiation that's out there. Radiation especially from the sun, but also from the earth and also from the moon. That mirror, in fact, there's 5 mirrors that are perfectly shaped, are the size of a tennis court. And you need to deploy that in space. Again, all this stuff does not fit in a rocket. So what you need to do is build an origami of types in which you kind of squeeze in all in a rocket and you deploy it into its magnificent shape that's out there. And then you need to look back in time. And frankly, many of these systems you can actually not test because there is no clean room that's big enough to have the whole system deployed anywhere on Earth. So that's what the job is we try to do. Now, what's really important when you look at that is that to recognize there are problems we look at, and many of you think about that also. They are bigger than one nation, bigger than one continent, and it's a humanity scale problem. And that's what I want to give you a sense for. You want to do big things like that, you need everybody. And in this case, we need basically most of the states in the United States 3 space agencies, the European, the Canadian space agencies, many countries that supply specific technologies that only exist there, and that needs to come together as a whole to do great things like that, whether it's about the universe, and I believe that having launched 37 missions, started another 60 plus missions, is a team. And it's not just a team made out of like-minded people. It's a team made out of people with different backgrounds and different opinions. And even a guy who grew up in the mountain, kind of in a small world, has a place in it. And that's what I learned as I did that. So that diversity of thought, that kind of clash of different type of opinions and different skill sets is one that is absolutely critical and is, in fact, I consider absolutely enabling as we look at big ideas like building a telescope like this. Now I want to tell you, this was really hard. In my last 6.5 years, I spent at least 1 to 2 days off per week, every week on that telescope. And when I joined NASA, I remember I went to these meetings and everybody told me everything is great. And they come with these stoplight charts. They were all green. Green on cost, green on schedule, green on technology. And roughly a month into it, I noticed, wait, that doesn't look like it's green. The words say it's green, and I took notes. And I want to tell you, it took me almost a year to notice that it's not only green, it's absolutely red. And basically what we had done is build a telescope that, frankly, had huge challenges. You see me there testifying to Congress. I don't recommend that. So, especially not when screws and washers are falling off the telescope. And of course, what happened, and that's the important part of building these teams, is what you believe as a leader only matters if you manage to propagate it into the team. We did not have the same attention, the same excitement, the same care all the way down at the technician level where that we had up there. In fact, we had many secrets in the team that we were not talking about. Frankly, the path forward was not easy. We got a final lifeline from the Congress for frankly, $800 million more after a tough fight. And frankly, I wasn't even sure we would be successful. I got an independent group and they said, you can be, but you need to fix these 32 problems. We fixed them and we tried to launch this rocket, and by the deal that was made long ahead of me, we wanted to launch it from French Guiana, which is in South America. That's where a rocket is launched by the Europeans that actually uses, kind of to a maximum extent, if you want, the rotation of the Earth, because it's so close to the equator. And we were there, and finally, on Christmas Day, this is what happened.
Standing by for terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And
Allumage
liftoff.
UAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
I want to tell her yes. I want to tell you why I love launches so much. First of all, it's not just that a rocket does what you know is really hard to do, because if you put a needle up on the desk, it wants to fall over. The rocket wants to do that too. So because of the control system and all the engineering that goes into it, the rocket goes straight up. But what I love about it, it's the ultimate act of defiance against gravity. I'm taking off away from the Earth, even though the Earth pulls me back as much as it can. And finally, 1.5 hours or so later, we saw for the last time the Space Telescope with our own eyes. You see at the bottom there, me clapping with masks. This is after COVID. And you see the telescope taking off. Do you see the ring there? That's how it was attached to the rocket as it came off. By the way, the only reason the camera was there is because 2 launches before, Arianespace had a major technology problem. And so we put the camera there to make sure it all worked. And to our surprise, not only did we see the telescope going away, just wait a little bit, all of a sudden you see the solar panel come out. The final step of that day, the final goal of that day, because if you have a spacecraft without solar panel, it's just a piece of junk. The spacecraft with solar panel, that's its power system, is a spacecraft that can in fact do these discoveries. You see it coming out right there. I remember sitting in that room, and around me, everybody was in tears. None of us expected that we would see that. It was a huge surprise, and we were in tears, of course, not only because of the amazing mountain we had to climb to get there, but also because so many of us had spent a large fraction of our time with this, and we'd always dreamt about achieving that goal. Those moments are amazing. By the way, December 25th is Christmas Day, and the French, Arianespace had never worked on Christmas Day in their history. Frankly, it was not me making them work, because I don't believe you can do that. I think people need to themselves figure out that this is important. And I walked around the room and this is where my French lessons from Switzerland helped, right? I went around and thanked them all for working that day. And everybody, they had taken a union vote to work that day. And everybody of them said, we did it for our American colleagues. We can go home that evening and celebrate with our families. We wanted our American colleagues who spend 3 months with us here in the rainforest can do the same. That's why we all work. See, when I talk about teamwork, that's what I mean. It's not about getting your own priority as the highest paradigm, but also making sure that your team's priorities are there as well, and you generously offer up your support. When I heard that, I knew we were a team that we weren't there before. Now, of course, for me, the problem was normally a launch is 80% of the mission risk, and the rest is 20%. In this mission, 20% of the mission risk was launch, and 80% was deployment. And I already told you, you saw the spacecraft, it was tiny, as compared to the total spacecraft, which is, as I said, a tennis court. We need to go through that unfold sequence, and we had made a plan. And there was the maximum plan. We told everybody will take a month longer. And we didn't need a single reserve day until we were ready. And in late January, we had a focused telescope with all 18 mirrors fully focused on one point, so it behaved like a mirror of the 21 feet telescope as it was made from a single glass. So before I want to show you a little bit of that new view of the universe and then engage in a discussion with Kiko, I want to just quickly explain to you why we look back in time. So of course, you look out at the stars, you look up around you, you see mostly stars of our own Milky Way. You see some planets and you see stars, and the Hubble Space Telescope really imaged those stars around you. I don't know about you, but most of my screensavers on my computers are Hubble images, right? Galaxies, beautiful things. Sometimes we forget that the first time we learned that there are other galaxies was at the beginning of the 20th century. We did not know that there are other galaxies before that, and that was discovered. Now, if you go back in time, by the way, why do you care about galaxies? You're made out of stuff of this galaxy and of other stars. Every atom in your body is at least 1 billion years old. And many of them, the origins, we just only learned in the last 10 years. For example, of platinum and gold, they come from neutron stars merging. So what I'm having here, pieces of neutron stars on my fingers, right? But if you really ask it about your history in a long sense, it started 13.8 billion years ago with the beginning of time and space itself, with the Big Bang. And we had not learned anything about these first stars and the first galaxies in our history before this telescope. So what we wanted to do is look back in time and see how out of this kind of ginormous release of energy in space and time itself did stars suddenly form. And that's what we're going to look at in new ways using an infrared telescope. So let's go on a journey, just show you a few images, and I will start with a friend of yours that I just talked to you about, Galileo looked at, which is Jupiter. You can see it, of course, with your own eyes, and this is the first infrared image of Jupiter. So you see it's Jupiter because it has that big storm on it, which was discovered almost 100 years after Galileo, but it has been there and has been changing. Everything in space is changing. And that's going to be a theme you're going to see. You see all these storms and swirls. It's a very turbulent atmosphere, just like the water as you look out of the ship, get off the turbulent eddies that are happening there. What you also see is that there are polar regions that are really bright. Why are they bright? Because they're particles barreling down from space and are heating it up. We can measure that heat right there. By the way, you see also that Jupiter has a ring. Remember how we always learn Saturn is the only one with the ring? Not the case. Jupiter has a ring. It's a moon that's spitting out, in fact, gas and basically forming a ring. So this is a first picture of Jupiter. The reason I showed you that is to tell you that the light as it was collected had taken 32 minutes to get to the telescope. So I'm going to talk about distance and time. So it took 32 minutes. By the way, if you look at the sun outside, the light that hits your eye took off the sun 8.5 minutes or so before that. So this one is 32 minutes. This one is a really exciting measurement of a first. So besides looking at the early universe, what we also want to look at is something that wasn't even invented or known before when James Webb was started to be conceived, and that is to look at planets around other stars. The first such announcement was in 1995, a year before my PhD. It was theoretical before that. What you see here is the best image of a Jupiter-type planet in our own galaxy around a star. This was about 6 times the mass of Jupiter, and you see it's a crummy image. But it's an image in different lights. And it's an image that tells you, yes, we can see these exoplanets. And by the way, as you're looking at the stars, what we learned in the last 10 years is for each star you're looking at, there's at least one planet. In my astrophysics class in the 90s, looking at a star, the question was how many planets per star? The answer was 5 to 10%. So there's 10 times more planets than the optimistic people thought during the time of when I did my PhD. So that knowledge is really out there. This is just a few hundred years. The light took a few hundred years to get to us. The next one is what I would call kind of a celestial hospital. So this is a place where stars die and where stars are born. You see all this kind of brownish stuff. This is the Carina Nebula. It's 8,500 years the light took to get here. Again, in our own galaxy. All the brownish stuff is stuff that dying stars were ejecting. So think of stars when they're dying, when they're done with their fuel, they're ejecting the outer layers. And in the middle, you see these bright dots that are kind of emerging. Those are new stars that are forming and new planetary systems that are forming right there in our galactic neighborhood. One of the most amazing sights, what we learned with this telescope already, is that they're not only just atoms that are floating around, like iron and carbon and oxygen, which are what life is made out of, but it's also already there a lot of molecules that are way, way more complex. Molecules that have so much complexity. When I went to school in the 90s, that was impossible in class. It's like, oh, it takes a long, long time to make these molecules. That's really late. No, they're already there, kind of at the end of stars, and they're ejected there. I want to show you another picture, and before I do so, I just want to remind you and ask, who knows the movie It's a Wonderful Life? Remember how Clarence, I think is his name, comes from the heavens, and it's one of those galaxies that I'm showing you. It's called Stephan's Quintet. Now, if you look at that light, when it took off to come to us, dinosaurs were still on Earth. So something like 300 million years, those galaxies came to us, that light came to us, and you see that just like stars going through lives and kind of stars interacting with each other, being merged, galaxies do the same. So beginning of 20th century, we didn't know of a single galaxy. Today, we know there's at least as many galaxies as stars in our own galaxy. So there's the big trivia question. If you took every grain of sand on Earth and asked how many stars are there in the universe, are there more grains of sand on Earth or more stars in the universe? It's absolutely clear now, more stars in the universe. Absolutely clear. So you look at those galaxies that are interacting with each other at the interaction fronts, and you see these brownish, that color again. In fact, kind of gases are colliding with each other, and stars are being ejected. So that light telling us a lot about dynamics of galaxies. So I'm going to show you one more image. Before I do so, I want to set it up. Imagine you have one grain of sand on your hand, and you stretch it out. And that grain of sand is covering the sky. You go to a really, really dark place somewhere, and I want to show you how that looks. This is a specific place that's called the Flying Fish. It's in a southern sky, and what I'm going to do is zoom in. I'm going to zoom in quite a lot. So that particular grain of sand is a really much, much smaller part of the sky than is an entire constellation. And you see it, kind of the high resolution, you see it pop up. Right there is a picture of that kind of volume of the sky. And you see in that picture, there are, in fact, if I counted it, something like 4,000 galaxies in that picture covered with one grain of sand in your outstretched arm. You see 2, 3 stars. You see the things with the big, kind of glare. Those are stars, foreground stars. So you always know they're from our own galaxy. Everything else are galaxies by themselves. And what I want to show you now is in that picture, the oldest object that we've seen. It's almost hard to imagine, but we're going to zoom into that little red dot. So that little red dot is right now, and it's being contested already, I want you to know, the oldest galaxy we've ever seen. So that little red dot came to be less than 500 million years after the Big Bang. So the light that you're looking at was in space all the way at the speed of light coming to our telescope for over 13 billion years. And it ended up on our telescope for us to see. So imagine the immense universe that this telescope reveals, a universe that's much more beautiful than anything we've ever seen, and a universe we can unlock by coming together as individuals, thinking about big questions, but equally importantly, building amazing teams that can make those kind of machines of exploration a reality. And with that, Keiko, I'd like you to come back up.
I tell you what, Thomas, on a boat full of a lot of successful people, you really know how to make us feel small. It's like almost uncomfortable when you realize just how big our universe is and how much is out there and just how small and almost like precious what we are doing in this moment. But I think kind of focusing on these images, Webb's been there almost a year now, right? What have we, I know we've talked through the pictures, but what are some of the big takeaways for the science community? And what are we hoping to really look forward to in the next couple years here as we get more and more data?
So what's really out there are publications and kind of knowledge that was mostly fed by things we knew before. What's really exciting in the next year or two is there's going to be new ideas that are fed by things we didn't know before we launched. But even now, many of the theories are already crumbling quite severely. So I showed you this picture. We did that just to show whether we can focus on a deep image. We already broke the record for age of galaxy with that one picture, which means it's easy to break the record. It's either enormously good luck, but we already know it's easy. So in other words, there's many more early galaxies than we ever thought. So the universe is way more successful building galaxies than we ever thought. And we don't know why. It could very well be one of the prevailing theories out there is we always thought that black holes are at the end of the chain. Like you start with matter, dark matter, you build galaxies, and then a black hole forms. It could very well be that this is reversed, that black holes come first. So that's one of the things we're puzzling over. So we're already crumbling that theory. We already found in exoplanets new gases we've never seen before. And the most important kind of measurements are happening this year, right, kind of as we go forward. So there's already a lot of new things that come out there. But I would say kind of a year, 2 years from now is the Nobel Prize caliber stuff. And I would be very disappointed if this doesn't win at least one Nobel Prize.
I'm sure it will. Yeah, the image is spectacular, and I know the science will be as amazing. It's been awesome to see the leap from Hubble to James Webb. I mean, you could compare the same two images. If you guys haven't done that, it's pretty neat because the sharpness. And by the way, with all of these talks about AI, these are real pictures. Like these aren't, this is not like some AI generated thing because you like your initial thing when you look at it is like, oh yeah, obviously AI made that. No, the universe made that. And that's a real image. But I start to wonder, okay, we made this leap from Hubble to Webb. What does this look like 10, 15, 20 years from now? What's the next telescope and what are we looking for next?
So the next new telescope, we haven't started yet, is one that I believe should focus on finding life on Earth-like exoplanets. And by the way, that's not just me who believes that. Kind of in a decadal strategy of the top leading astrophysicists done by the National Academies, that is the highest priority. Now, what I really believe that what should happen is not that we're doing it the same way. I sat there at the launch. And frankly, the day before, I took a picture with the CEO of Arianespace and the guy in charge of space transportation at ESA. And I took a picture and said, let's take the picture just so we can say all the jobs that will become free if the launch is not going well, right? Because every one of us will lose a job because we have $10 billion sitting on top of one rocket. I mean, that's insane, right? It's the ultimate, like go to the casino. It's the ultimate,
3 minutes of like ride or die, It either goes really well or really, really bad.
Yes, and you know that, right? And then for me, like I became a pretty good stoic, right? So I visualized the rocket going into water and I wrote speeches to explain what happened, right? Because like it's a lot easier to deal with risk if you think about it. So what we want to do in the future is not that. What we want to do is build more like a mountaintop observatory. And in part, it's because of the work you and your friends have been doing, which is making launch more affordable. So what we can do is build a rocket, a telescope, which does not have to be that tailored. So we build it up there, we build it with robots, build it together, and we go improve it as we go. So we build a really good mirror, but we improve it as we go. And my hope is in the next 10, 15 years, we build that. And then we go after really finding life in other planets like the Earth in our own galaxy.
So what do you, based on the pace of innovation and technology, do you think it's possible we will gain a higher confidence that we're going to find presence of life in the universe within the next 20, 30, 50, 100 years?
I would bet my house on 20.
Wow.
So, and
20 years.
I'm talking about life elsewhere outside of the Earth. By the way, I'm saying that because of the rate of progress we've seen that is there. Of course, there's a number of things I don't know, but kind of what we've really seen is that, look, since, and I indicated that when I got all my astrophysics class, it's really instructive to look at the class notes and kind of see what's wrong today. So if I looked at so I don't know what the likelihood was of finding life in the universe in the mid to late 90s. I know it's 1,000 times bigger today. And I gave you some of the factors. There's more planets. It's actually easier to make chemicals. It's actually easier all these steps are there. There's a number of things I don't know. And of course, I may be totally underestimating. Sometimes you hit a major hurdle. But if you look at the progress, this is one of the most exciting problems. And frankly, we're going like in 5 parallel routes to Mars, to Titan, to Europa. You're going to launch the Europa Clipper, right? And then this exoplanet thing. So we're going in all these parallel things.
It's almost like we're on potentially this exponential knee where all of a sudden our rate of learning and our rate of discovery will be much sooner than we could ever imagine. I mean, the idea of knowing or finding out that there is life in the universe outside the Earth in my lifetime is honestly something pretty astounding to think about, or the lifetime of most of the people here. So that's very exciting. So we're very thankful for your guys' work on that.
Thanks.
I wanna switch gears just a little bit to what it meant to run a team at NASA. So you were one of my favorite professors. You're the first professor that ever gave me honest feedback that I kind of sucked at what I did, and it wasn't just about my grades. I needed to work a little harder, which is the first time you get feedback, right? In school, when you go to school, the only way you get feedback is your grades. No one actually tells you you're like good at something, not good at a thing, right? So Thomas was the first time someone sat me down and said, dude, you're not that sweet. You got things to improve upon. And you were you were a hard-charging professor. You started the School of Entrepreneurship. I thought you were going to start a company, and instead, here you go diving into, a bureaucratic government job, right? And that's a huge mindset shift. So, what are some of the philosophies you try to, the sort of entrepreneurial mindset you try to instill when you took over really many thousands of people across the entire country, really across the world? And, how did you proliferate that culture? Like you mentioned when you talked about James Webb, how did you get that messaging all the way down to the technician? What are some of those philosophies and methods?
Yeah, so I told you where I'm from, right? And, what I didn't tell you that I grew up in an Amish community. So eventually I got ejected from that. So I'm all about breaking down boundaries. And for me, there's a lot of people who told me I'm not smart enough to go to university, right? And so I know when people tell you that, don't listen. Yeah. I mean, whoever you are, people tell you you're not smart enough, don't listen. Because that is a really bad feedback, and usually it has not worked for anybody. And so for me, the reason I gave you and everybody else feedback, because I think the biggest tragedy that happens in life, and that is with organizations too, that you come towards the end of life and you realize that you were driving a car, metaphorically, and you were driving in the first gear. There were 5 more gears, you never used them. And for me, what I really wanted to do, whether it's with you or everybody else, including my NASA team, is to kind of push enough so they go to the other gear. Because once you're in that higher gear, once you realize, well, I can perform more, I can do this. I never thought I could do this. We're all kind of, as a community, as a society, we have more potential for solutions, and we need those kind of problem solvers and kind of opportunity recognizers out there going for it. And for me, it was really important to bring that to NASA. And that is the ultimate entrepreneurial mindset, I believe, recognizing that something that looks impossible is absolutely possible if you work at it and if you build teams to do so, even though you don't have all the tools to actually make that happen. It helped me also understanding how companies work, because so many of my good friends at NASA had never worked in a company, right? So they didn't actually understand what's possible in a company, and had looked at this that way. But for me, it really was the sense of recognizing that excellence and very good are worlds apart. Right?
Yes. Preach.
Yeah. And the fact that individuals can make a huge impact. So let's empower them and let's make it happen.
Awesome. So one thing that's always fascinated me, like, you mentioned you had to go get $800 million to finish the telescope, and we spend $10 billion on it, which is an astronomical number to do science. The learning and the fundamental knowledge we gain from science has such value to us as humans in society. But it isn't capitalism, right? I can't pitch a science project in the same way I could pitch a company that creates value, right? And I've always wondered, how do you sort of make these two worlds or should you make these two worlds intersect more in an effort to effectively drive more funding and accelerate our pace of innovation and accelerate our pace of learning about the universe, or really fundamental science or physics for that matter? So, your thoughts?
Yeah, no, I mean, I think it's both a good question, but also a hard one. So I want to just quickly ask, why do we do science? And I think there's at least two reasons to do science, and they're very complementary. They don't exclude each other. The first one is kind of science teaches us more about the world, about ourselves, about our history, about our future, and kind of out nature. And I don't know about you, but if I look at nature, I go on a mountain, I look down, it feels important. I don't know about you, but I was in the gym today and I saw two dolphins, kind of breaking through the surface and going back down. I'm like, wow, I wish I could follow them down, right? Because the world that they're in is so different and I'd like to learn more. And for me, curiosity is really, driving science. It's just a wonderful thing. Science is also providing solutions and opportunities for the future. In many ways, the problems we have today, whether it's with our own climate, whether it's kind of how we stewardship of our own most beautiful planet, we've observed like many of the solutions come from space. And of course, we didn't think of that when we launched. We wanted to build the Soviets to the moon. That's why we did it. But the solution space that comes from that, look, if you basically said, what do we know about climate? The vast majority of climate data sets that you're looking at come from space, whether it's sea level rise, kind of overall temperatures, deforestation. Of course, there's local data sets that really matter, and all climate change is local because that's where action is delivered and kind of is implemented, but nonetheless, space is so important. So I think of the future, right? What are the problems we want to solve in the future? I don't know yet, but science will provide that toolbox. Now, how we bring those together, I mean, it's equally hard in business itself, right? If all you're focused on is the next quarter without looking in the future, first of all, you won't have a long business life, generally speaking. I mean, there's a lot of challenges with that. So the question really is also kind of, how do you bring in large trends? You're working with SpaceX, we're going to talk later, right? Kind of, how do you bring that big vision, make that happen in a place where kind of many of the stakeholders that are in right now are focused on the next quarter. We don't get to the big ideas that way. So that's why I'm such a champion for small companies taking enormous kind of big leaps, trying to really kind of push them into new ground because they have more opportunities. So for me, the science is important. There's a lot of business opportunities in science, but it's just as important to kind of see this part of kind of a broader view, which is also important in business as we look at it today.
You mentioned Earth observation and the work you did in the agency, and obviously our efforts to try to understand and help fight climate change. One of my biggest concerns is that when I look at the general constituents of Congress or the House of Representatives, there are very few. I think there's maybe one or two of all of our elected officials that have a science or an engineering background, right? So you don't really have that knowledge in the policymakers. How do we manage that? And how did you manage that? And how did you help make sure that, how did we create that influence? And I know you have a specific story to share about that after the 2018 election.
Well, so for me,
16.
First of all, I really believe that service should be part of value that we have in our communities, doing service. I mean, for me, like when I went to NASA, I took roughly a factor of 2 pay cut. And I was glad to my wife and our family to kind of enable that, right? So it's a smaller house now, but I do service for the government. I was never going to stay there for my whole life, but I wanted to do something for this country, which I call my home, and serve there. So for me, the question I always ask, in a science community, do we value service? And of course, you look at where the rewards come from so often, not enough. The other piece that's equally important is that we're all voters, those of us who live here in your countries. What are you doing to reach out to the elected representatives? I spend a lot of time in offices of elected representatives, and also the difference between the on-camera persona and behind the camera. And I remember when the first budget came out under the Trump administration, Earth Science was slashed, right? And I had spent quite a lot of time with both Republicans and Democrats, which is my job. One of the Republicans was the first one, the leader of appropriations in the House, came up and said, we're not going to do that. In Texas, we need Earth Science because there's a lot of threats there. Look at the hurricanes that are coming. We're not going to cut Earth Science. And so what happened is, of course, a lot of these cuts never became reality because of support from many others. So for me, discussions with stakeholders matter. So it's easy to be sarcastic and stand at the sideline and kind of make everybody discouraged. But it takes courage, I believe, to tackle these problems and frankly, take a plane to DC and kind of go actually engage with some of these individuals and explain to them why it matters.
I think that's really important. Like a lot of the people in this room, may consider an opportunity in public service later. And at the end of the day, the policy is what's going to drive our ability to let capitalism go to work too on doing the right thing, which I think will be key for climate change. So I have one last question, because most of us here grew up in the generation where Pluto was a planet, but they've taken it out of the textbooks as a planet. My 3-year-old, when I read the books, there's only 8 planets. So Thomas, let's settle it right here. Is Pluto a planet?
So I bought a necklace for my wife with all the planets on it, and I said, I want one without Pluto.
Oh, you heard it here first.
But here's the way. Look, this is about, like, you tell me, I'm perfectly fine if Pluto's a planet, but let's go backwards. If I said today, let's figure out, with everything we know today, what is a planet? Pluto would never be a planet. Because why? There's 50,000 objects out there in the Kuiper Belt, and some of them bigger than Pluto. Pluto was just the first one we discovered, right? So they're all planets, but they're small planets that are out there. They're a really important part of the history. And frankly, the outer solar system kind of is full of these kind of objects. But the point is, if you knew what we know today, you would have not called them a planet. I have zero problem if people want to call them a planet, but for me, I said, the head of science, I cannot have her.
Totally fair. Okay, awesome. Hey, so we got 12 minutes left, and I figured we would open it up to the audience for some questions. You've got your hand out there right now, so why don't you, hopefully we can hear you. Crazy facts.
Well, I'll start with my rings. So I already told you, that most of that gold and most of platinum is formed in one specific type of stars that are neutron stars. We actually thought they're coming from explosions of stars. We proved in the meantime it's not the case. So we've only discovered one merger of 2 neutron stars. We discovered it by ripples of space, gravitational waves. And just by accident, we managed to look at it with a gamma ray telescope, and we found lines of gold and platinum that basically tells us that theory, which was a minor theory, is in fact there. So that's here's one of the facts. I think the other one I mentioned, I wanna just reiterate is that for every star in our own galaxies, there's something like 400 billion stars. There's a galaxy by itself. And remember, 100 years ago, not one other galaxy was known. My guess is that number will go up. So we may have, instead of similar, kind of when I did my PhD, it was a big question always, and nobody knew how many grains of sand on our beaches, and the stars, they looked roughly the same. It may be 100 times more stars. The third fact I want to tell you, I did not talk anything about, which is we know with 100% certainty that we only understand 5% of the energy in the universe. So 5% is matter, like you and I are made out of, and things we can detect in the lab, like neutrinos and things like that. Roughly another 20% or so is what we call dark matter. So we know it's there because it bends light, it changes the orbit of stars and galaxies, but we don't know what it is. And the rest is dark energy. So it actually is so important, so strong that it actually accelerates the expansion of the universe. When I went to school, the only two solutions we looked at are universes that collapsed on themselves after so and so many billion years, or the ones that stayed the same. This one, the universe we're living in, is one that's accelerating, driven by energy we don't understand. And so we only know 5% of the energy. We can actually understand only 5% of the energy in our universe. And that is quite concerning for me.
I was going to say, I feel like someone's going to tell me that at 3 a.m. at the Haven or something like that. Yeah, sure. Let's go right here.
The photograph you showed from the nebula, the Star Hospital, the colors that we see, are they, is that like a color photograph, or do you color them now?
So he's asking how the color that we see, is it a color photograph? So we're struggling with that, right? So here's the problem. Your eyes, again, if you stood in front of it, you would not see it. You would see only the stars because they have a optical counterpart. So what we're doing is in each one of those telescopes, when we're deciding how to color them, we actually hire artists, first of all, people who really know, and we talk a lot about the kind of science of it. And I want to tell you, I love working with artists. Some of the best ideas I got from artists, right? Art is a good way of perceiving the world. So what we're doing then is coming up with color scales that are like you would guess. So blue is higher energy than red, but the way we're setting it is to color the whole range that the particular telescope has. So it's physically correct in that sense, but it's fake color in another, because your eye would not see it that way. So there is artistic interpretation in the sense that the allocation of color to a given wavelength range is in fact decided by somebody, actually decided by a handful of artists that work together with scientists. And we try to do it as honestly as possible. So at the end, your impression of it is correct scientifically. So we go back and forth until we're in sync. So we're not trying to fake you into believing something that's not there, but trying to be as trustworthy as possible, recognizing that your eyes don't see it.
Big question, yeah, right there.
Thank you for inviting us today. I'm wildly fascinated by your conviction that in 20 years we will discover life out there beyond us. And it gets me thinking, if you're head of NASA 20 years from now, we discover this, what happens next? What are some of the tactical steps that you can take to try to reach out or interact and communicate?
So you're asking, after discovering life, if I was head of science 20 years from now, what are the tactical steps that I would take? So first of all, I think it would be one of the most exciting times in science overall. I mean, in many ways, it's
a humanity, just straight up.
For humanity, because it's a Copernican revolution of the next kind, right? That's the dream you always have, breaking through a major wall of ignorance. Our gut feeling was always that there are planets out there. We found them in 95 for the first time. Now we know every star has a planet. So that transition from a chemical, physical world to a biological world, I think it would spur a whole kind of new innovation, the likes of which is really hard to predict, because perhaps the right medicines for us are in different life forms elsewhere. right? Kind of like ways that kind of we, with our DNA-based life, the one life that we have, we cannot reach. For me, what I would really want to do is get the maximum kind of knowledge out of it right away from both sides. Kind of remember, when you look at the future, and there was an AI panel here before that, when you look at the future, hope and fear are always close to each other. The same is true with this one, right? You'd want to make sure that you understand the fear side of the equation and the hope side. So I really want to make sure I go after both and understand in what way would that life interact with us. Remember, what I'm talking about is microbial life. I did not talk, as of yet, for intelligent life, which is a lot harder to predict, by the way. I don't know. Somebody said they're already here.
They're on this ship.
Yeah, recently a guy, I told you recently, a guy in an audience in New York told me there are 3 spacecraft that are following me around. I'm like, he sat in a room like this. It's like, where are they? But not, you know, so I don't know about intelligent life. That one is actually a harder problem we can talk about, in the future. But for me, I would like to be science director in 20 years because it's like the most fruitful kind of, it really, a new book opens of exploration. I'd like to go after it with everything I have, you know, not as an agency, as a person, but as a world, and really say, hey, what are the opportunities that are there?
Yes, green shirt.
Yep, you. Besides finding life, what other things or discoveries within the next 10 or 20 years do you think have the potential of changing both our culture and our understanding of the universe?
What are the changes in the next 10, 20 years that change our culture, our understanding of the universe?
Besides finding life.
This one is the biggest, right? It's hard to kind of, it's shining so bright. I'm trying to focus my eyes on something else. Well, look, I do believe, so what I'm spending time on right now mostly is trying to figure out kind of the big challenges that we have today that could really change humanity. The one that I'm focused a lot on is the health of our own planet. And the question just really is, in the toolbox of everything that's available, what are the tools, including the ones that come from space, that could help us kind of be more aware of what's happening on Earth, but also really, if you want, almost create an exoskeleton in space for our own planet, right? Kind of a support system for our own planet. So for me, that's a big idea. So what I'd really like to do is almost in a near real-time sense, not the way weather comes down. I'd like to inform you about kind of decisions that you're making and how it's affecting things around it. So often we think of climate as something that is not affecting us. Okay, last year, so since 2020, there were 2 500-year floods in Florida. 500-year floods are defined by the statistics of the past and are used for insurance or reinsurance purposes. Florida has
someone who lives in Florida,
you know about it.
Sucks here.
Yeah.
For
so
sure.
9% of all the properties in the United States, insurance is in Florida. 74% of all claims last year were in Florida, right? So kind of, you say, well, so many people's like, well, climate is not affecting us, it's affecting us today. So I haven't figured out yet, and I don't think, there's good ideas out there, and many of them in the entrepreneurial world. I'm really excited about Planet Labs, for example, Spire and other companies that are really saying, hey, we want to image the Earth, kind of really provide that information near real time here. So deforestation somewhere else is recognized and can be taken into account. So that's a second idea, really, that kind of exoskeletal support of our planet in space. And I'll stop.
So we're almost out of time, Thomas. Any last thoughts you want to lead this group of entrepreneurs and creatives and people that just want to go change the world?
Well, look, I really am excited to be here with you because you inspire me kind of in many ways. The ideas that you have, whether you're artists or people who care deeply for others or build companies, are kind of what brings us forward, and in many ways, it's the same force that creates telescopes like this, right? And so for me, recognizing that at the end, it's basically humans that do it. I love, like, perhaps one of the hardest lessons I learned. I went into NASA science and I thought 70% of all problems that I'm going to solve are technology and 30% are going to be people. Reversed. 70% of all problems I solve are people problems, team problems, coming kind of imagination, kind of what is the scope in which we're thinking. And, technology will figure out eventually. So for me, what I really believe in and what I'm so excited about here with all of you here is just really, do not accept those boundaries that are ahead of you, and recognize that the world of possibilities is much bigger than the world of reality that we live in today.
Awesome. Thank you so much, Thomas. This is super special.
Thank you.